compress the contents of any shipment so that more units can fit in the limited space available. The compression of physical objects has been going on for some time now. Foodstuffs, for example, can be compressed by removing the liquid content. The cook merely has to add water in order to reconstitute the food item to its original state. The term UPS shippable also comes to mind. Many products are now shipped in a compressed format, in other words, unassembled, and the goods are decompressed or assembled at the receiving end. The concept of electronic compression was first used in computer systems to solve critical data storage problems. A single floppy disk like this can hold about 250,000 words of text. In the early days of personal computing, this capacity was sufficient for most applications. But as the ability and complexity of computers and peripheral devices has grown, so has the size of the data files that we need to store. To solve this problem, computer programs have been created which convert data files into an equivalent shorthand format that preserves all essential information. Through compression, a file containing 500,000 words can now be contained on this same single floppy disk. To reuse this compressed file at any future date, the computer operator uses a special program to expand the file to its original format. In two-way communications networks, compression is used to reduce the amount of frequency bandwidth without substantially degrading the quality of the message. In order to understand the concept of bandwidth, we must first have a working knowledge of the term frequency. A frequency is defined as the number of times that an alternating current goes through a complete cycle in 1 second of time. 1 cycle per second also is called a hertz, named after the 19th century radio pioneer Heinrich Hertz. 1,000 cycles per second is called a kilohertz, 1,000,000 cycles per second a megahertz, and 1 billion cycles per second a gigahertz. Every communications channel has a finite amount of frequency spectrum or bandwidth available. For example, a typical satellite channel bandwidth would be 36 megahertz wide. A single cable or broadcast TV channel bandwidth would be 6 megahertz wide, and a narrowband telephone channel just a few kilohertz wide. Compression dramatically reduces the bandwidth transmission requirements so that multiple signals can be transmitted within the same space formerly required to send just one signal. All communication signals were formerly analog waves of electromagnetic energy which conveyed information by changing both the intensity or amplitude and the frequency of the waveform. During the past 10 years, however, narrowband communication systems such as telephone networks have been converting their transmission formats from analog to digital. Through digitization, signals can be expressed as strings of zeros and ones, binary numbers which correspond to the off or zero and on or one logic states of computer circuitry. In digital sound transmission systems, audio pitch and intensity are expressed as a stream of binary digits or bits. A transmission rate of 1,000 bits is called a kilobit per second, while a transmission rate of 1,000,000 bits is called a megabit per second. While analog audio transmissions are sent continuously in real time, digital audio transmissions are sent in bursts of pulses, which are then stored in the receiver's buffer circuit and released over time to maintain an uninterrupted flow. Digital transmissions offer several advantages over their analog counterparts. As analog signals pass through a system, they will pick up noise from each of the amplifiers in the communications chain. This can degrade the quality of the received signal. Digital processing converts the original message into a numerical form that is not susceptible to this kind of degradation. Each group of numbers or block within a digital transmission can be numerically checked at the receive end. Transmission errors can be detected and in some cases corrected, or in other cases masked so that they are not perceived. Digital transmissions therefore have the ability to deliver a more faithful representation of the original signal. During the past decade, telephone companies the world over have been converting from analog to digital. The result? Higher signal quality and lower cost due to the reduction in signal bandwidth. Digital video compression offers several distinct advantages over analog transmission systems. Compression can be used for many applications regardless of the transmission format. Multiple TV services can easily be integrated into a unified signal. This gives service providers a convenient way to process subscription requests, deliver TV guides, and other information services. Digital video compression will also provide services with a high level of encryption security to prevent unauthorized reception. Video with stereo sound, auxiliary audio services, text, and data can be integrated into a single unified transmission. What's more, sophisticated error correction techniques can be used to produce pictures free of ghosting, snow, and other interference that often plague analog broadcasts. During the 1970s, the world's early planners of direct-to-broadcast satellites thought that 3 to 5 channels of television would be more than sufficient to meet consumer demand. But once millions of American households began receiving dozens of channels using big C-band dishes, the game was over.
And it's very interesting to me that C-band has really taught us and taught the world a lesson. And that lesson is that all of the old planning for 3 to 5 channels of television was simply baloney. People won't buy 3 to 5 channels of television because they've had the experience now with cable, where they get 30 to 60 channels. They've had the experience with C-band, where we at times have 200 channels of video. That's what people see and that's what people want.
In 1988, the International Standards Organization, which operates under the auspices of the International Telecommunication Union of the United Nations, established a technical committee known as the Moving Pictures Experts Group. The MPEG committee's task was to create an internationally recognized worldwide standard for the compressed representation of multimedia. The MPEG committee initially developed a standard for a wide variety of non-interlace or progressive scan sources of multimedia, including text, graphics, photos, audio, and motion pictures. The model for this MPEG-1 standard was finalized in 1992. MPEG-1 currently is used by CD-ROM computer storage devices, which operate at a bitrate of 1.5 megabits per second. MPEG-1 also can accommodate the storage and transmission of video at higher data rates. MPEG-1 was not designed to transmit interlace video signals. However, MPEG-1 can process interlace video by first converting it to progressive scan video at half the normal field rate. Early digital video compression systems developed by Compression Labs and others have used a modified form of MPEG-1 to develop satellite distribution systems now used by business and broadcast customers around the world. In 1994, the MPEG committee finalized its criteria for a new MPEG-2 standard governing interlaced video applications. With MPEG-2, the resolution of the compressed video has been dramatically increased. Bit stream rates of up to 40 megabits per second also are possible, fast enough to accommodate a high-definition television picture. The worldwide adoption of MPEG-2 as an international standard was the key for making today's 1,000-channel universe a practical reality. By comparison, those old 3 to 5 channel systems look downright quaint. This new compression technology dramatically lowered both the cost and complexity of satellite-based networks, because less power was needed at both the uplink and the downlink sites. Dishes could therefore be smaller and less expensive than had previously been the case. DBS had become a force to be reckoned with.
Digital compression really is the enabling technology for DirecTV. Previously, you could only send one clear video signal through a satellite transponder. With digital compression, we can send up to 8 video signals per satellite transponder. So with only 2 satellites in orbit at one location, we'll be able to have 150 channels of programming, and again, all available through a small 18-inch fixed satellite dish. What the consumer will see is a crystal clear picture close to Laserdisc. They'll get CD quality sound. There'll be this innovative on-screen menu that'll be transmitted as well, so they can sort through the programs. So it's really going to be a whole new experience for the consumer. In addition to video, we'll be able to deliver data services such as stock market reports, weather reports. Potentially we can download computer software to a storage device, games. It just opens up the whole world of digital transmission, which means computer data, possibly interactive services down the road. So this is a whole new world we're entering into, and all available through this small 18-inch satellite dish.
And for us personally, it turns a 5-transponder business into a 25-some channel business. Clearly the economics are very different if you're not in the digital compressed environment.
Finally, the merging of digital and computer techniques with television. It's going to change television as we know it. It's going to increase transponder capacity. It's going to allow us to reduce antenna size. It's going to allow us to change our attitude about how we use a transponder. For instance, instead of putting a movie on that runs twice a day, we can put the same movie on the transponder in 10 places but running 15-minute intervals. So anybody can dial up and know that they're going to be able to watch a movie that starts in 15 minutes on a pay-per-view basis.
Once you get into the digital domain, you end up with a tremendous amount of flexibility, or the potential to have this flexibility. In the newest generation of compression systems that various equipment manufacturers are talking about, you can basically mix and match different types of services in the same multiplex, whereby a customer with one antenna can receive radio services, TV services, different types of multimedia services, all from potentially one box if that box is designed correctly. The other issue that is very, very big in all of this is that because of the flexibility of all of the compression systems and the way that all of these bits get multiplexed together to get a digital pipe into the customer's homes, the programmer also has a tremendous amount of flexibility in launching new types of services.
There is only a fixed amount of data capacity that you can get into a given satellite transponder. But within that overall fixed capacity, the programmer or whoever is actually operating the system has the capability, simply through a software package which we have designed, to go in and indicate that channel 1, for instance, from 8 p.m. till 10 p.m. is going to be a basketball game, and from 10 p.m. till 1 a.m. is going to be a movie. And what the programmer can do is not only indicate within the system when the various programs need to come on, but he can also program the system such that he is using much greater bandwidth for the basketball game, which is very high motion, and then can take it down to a lower bit rate automatically within the computer system for the movie, and then reallocate those bits perhaps to another basketball game which may be showing on channel 5, which is in the same transponder. So the system is extremely flexible for the operator. And we have already seen people like Turner Broadcasting, for instance. They have TNT, which does basketball. They have TBS, CNN. They can put all of those into a transponder and then mix and match the bit rates as required amongst those services. And the same is true for programmers worldwide.
The convergence of so many different forms of media into a single worldwide format is the exciting part, because you're going to have so many efficiencies that you're going to have much more programming, which will be attractive to more consumers that they are willing to pay for this product. It's going to offer more variety, more choice in a more efficient manner, which will have a happier consumer and therefore, sell more products.
Everyone internationally who is looking to try to implement new digital video services, their #1 requirement is that it be MPEG-2 compatible. It's the fact that they are also seeing that, hey, in the future, if I want to get video direct from a D1 machine, I'm going to be compatible with it. If I want to receive compressed video from another programmer to rebroadcast, if I'm MPEG-2 and he's MPEG-2, I'm going to be able to receive that without a lot of extra equipment to decode it and decompress it and then recompress it back into the standard that I'm using. And I think it's the future compatibility and the promise of what the future holds for what programmers can do that is leading them to look to MPEG-2 as a savior, so to speak. They're not going to have to worry about NTSC to PAL conversions or SACAM to PAL conversions anymore.
Programmers can compress their program material so that it can be stored, transported, and reused by any MPEG-2 based system without further conversion.
A broadcaster has the advantage under MPEG 1 and 2 that he can take material that has been pre-compressed from almost any source, as long as it's been correctly compressed in the MPEG format. And even if it's MPEG 1, he can broadcast it through an MPEG 2 system. The receivers and the receiver chips that he'll be broadcasting to will be capable of decoding a good picture from that compressed broadcast, no matter where it was compressed or who compressed it.
In North America, the standard TV signal consists of 525 scanning lines per individual image or frame. Flashed at a rate of 30 frames per second, each frame has 2 alternating or interlaced fields consisting of 262.5 lines each, with field 1 consisting of the even-numbered lines and field 2 the odd-numbered lines. The speed at which the fields are transmitted, however, is so rapid that the eye perceives the image or frame as a whole rather than 2 separate components. In Europe and elsewhere overseas, other higher resolution video standards with 625 scanning lines are used, which display images at a rate of 25 frames per second. Like the American system, these other standards use 2 alternating or interlaced fields. A single frame of 525 line NTSC video is composed of more than 150,000 picture elements or pixels. Since video operates at a rate of 30 frames per second, more than 4 million pixels are being sent to your TV screen each and every second. A maximum of 32 bits per pixel, 8 bits per brightness element, and 24 bits per color element would be needed to digitize a full motion color video image in an uncompressed form. This translates into a transmission rate of 128 megabits per second, enough to fill a wideband satellite transponder to capacity. MPEG-2 compression dramatically reduces the number of bits per second which actually need to be transmitted. This is accomplished in 4 ways: through pre-processing, temporal prediction, motion compensation, and coding. Through pre-processing, video information which is not essential to human visual perception is filtered out. Early studies of human perception have established how individual components of a video signal must be transmitted in order to maintain fidelity with the original image. For example, lower frequency video information is more perceptible to the human eye and therefore is more critical than the higher frequency information. The assignment of bits can be prioritized at any given moment according to which blocks need them the most to maintain the maximum perceptible image fidelity. Video sequences are highly correlated in time, with each frame in a sequence quite similar to both the preceding and following frames. It is therefore unnecessary to resend the parts of the image in which no elements have changed. The basic unit used for motion compensated prediction is called a macro block. A macro block consists of 4 8x8 blocks of pixels containing the luminance or brightness data and 2 corresponding 8x8 blocks of chrominance or color data. The encoder economizes on bandwidth by instructing the receiver to recall a previous frame's unchanged macro blocks from a buffer storage circuit and reinsert them into one or more subsequent frames. This requires substantially less information or bandwidth than sending all frames in their entirety. Motion compensation is used to compute the direction and speed of moving objects within the video image. All macro blocks are scanned to identify those portions which will not change position. Predictor blocks also are identified, with their position and direction of motion noted. Only the relatively small difference, called the motion compensation residual, between each predictor block and the affected current block is sent to the receiver. If all of these differences are communicated directly to the receiver, then no distortions or artifacts will be visible in the displayed image. Artifacts will be introduced whenever there is an insufficient number of bits available to communicate essential image information and rapid motion changes from one frame to the next. In this case, it is a trade-off between bit rate and image fidelity. MPEG accurately predicts where a moving object should appear in each succeeding frame using a very small number of bits. Moving, yet relatively unchanging objects are reduced to a mathematical shorthand equivalent of take the same object from the initial frame and move it 3 macro blocks to screen right for the next frame. Objects which change shape and move at the same time, or multiple objects which are moving in different directions at different rates, do not compress as easily. These objects therefore require a larger assignment of capacity in the bit stream. Whenever major scene changes occur, the encoder must instruct the receiver to dump the blocks from the previous frame stored in the receiver's frame buffer and transmit an entire set of new blocks. The frame being coded is predicted from previously coded frames. The difference between frames is transformed using a mathematical algorithm called the discrete cosine transform, or DCT. The DCT can reorganize digital blocks of pixels into an even more compact form. Each macro block is first divided into 4 sub-blocks of 8x8 pixels for spatial compression within individual frames. The DCT algorithm converts these sub-blocks from a spatial domain into equivalent numbers in a frequency domain that can be transmitted more quickly. The DCT views the 8x8 block of picture information as a varying signal that can be approximated by a collection of 64 cosine functions. Each cosine value is associated with a DCT coefficient, which represents a different frequency component. Quantization takes these frequency coefficients and converts them to more compact codes, representative numbers which take less bits to send. The encoder accomplishes this by searching an internal codebook, a collection or index of possible representative numbers, and then selecting the code word that best matches the original set of frequency coefficients. Quantization approximates the original image in a subjectively acceptable way by rounding off all values within a range of limits to the same value. In 1950, Dr. David Huffman developed a unique coding system for compression. With Huffman coding, relatively probable messages are assigned short numerical sequences, while relatively improbable messages are assigned long numerical sequences, resulting in a data compression factor of 2. This coding is often compared to Morse code, which effectively represents alphabetic and related symbols by signals of varying lengths. The key is to use shorter codes for the things that are more likely to happen. The shortest code in the Morse system is a single dot, which represents the letter E, the most frequently used letter in most text. Longer combinations of symbols, dots, and dashes are for letters like Q, X, and Z that are not used as frequently. Therefore, the idea of variable length coding has been around for a long time. Dr. Huffman used this concept to develop the best variable length code to work under very general circumstances. MPEG provides for 3 different types of video frames which can be coded into a digital bit stream. The first frame in any video segment is called an intraframe or I-frame. The I-frame is coded using only information presented within itself. No reference is made to other frames within the digital bit stream. I-frames occur on an average of 1 out of every 10 to 15 frames, or whenever there is a scene change. MPEG uses the I-frames as a reference for predicting 1 or more subsequent frames. P-frames are predicted frames with reference to information presented in the nearest preceding I or P frame. Each P-frame also serves as a reference for future P-frames. B-frames are bidirectional frames that are coded using motion-compensated prediction from the nearest preceding I or P frame and the nearest following I or P frame. The sum of the bits assigned to the I, P, and B frames cannot exceed the allocated transmission speed in any given second. Not all MPEG-2 systems use B-frames. Those systems which do employ B-frames achieve a more efficient level of compression by up to 15 to 20%. Less data, therefore, is needed to achieve the same video quality. Decoders using B-frames, however, must have a second frame buffer. This adds to the cost of the total system.
Compression is very much like what everybody's used to in Name That Tune. It's how many notes do you need to be able to tell what the song is. At 8 notes, most everyone can guess what the song is. But if you only have 1 or 2 notes, it's very difficult. If in the B-frame implementation, you only need the 1 or 2 notes to be able to accurately predict what that tune happens to be. That's the advantage of compression.
In order to support the use of B-frames, the encoder does not transmit the frames in display order. Instead, the encoder holds many frames in its buffer, figures out the best pictures to use for I and P frames, and then codes them out of order. Real-time encoders have a finite amount of time in order to make encoding decisions. Some compromises, therefore, must be made, either allowing more picture artifacts are using a higher data rate for the transmission. Non-real-time encoders for movies and other taped material do not suffer from these time constraints. The encoder can slow down and take its time when processing the image to select the best possible method of encoding. This results in a lower data rate for the same quality picture. Live sports and other live action material also require a higher data rate. More bits per second are required to transmit complex, rapid motion changes without introducing high levels of distortion. Different data rates will be used by the MPEG-2 video encoder depending on the nature of the video source material to be encoded.
The first clip we'll be showing is a sports clip, which will be done at a high data rate of around 8 megabits. We use a resolution of 704 by 480 for NTSC or 704 by 576 for 625 line PAL material. This will be done for high quality sports, fast motion type applications. The resolution is full CCIR 601, which has the 422 sampling and is used for broadcast to contribution links for retransmission. This will be used throughout the industry as we move on into the MPEG-2, and we have the new MPEG-2 algorithms as they continually evolve. The next clip will be a 544 by either 480 or 576 with vertical resolution. The data rates that will be ran at this resolution will be between 5 and 7.5 megabits, depending on the application and the quality you would like. The applications will be for redistribution, and again, at these data rates you can handle high-speed sports, good general entertainment quality, and this will be good for any type of home distribution type system where you want full luminance resolution. The next cut will be 352 by 480 or 576. The luminance resolution on this is about 2.5 megahertz, and this is good for general entertainment, news, documentaries, and all types of information that you do not want to give full resolution to. A number of the movies that are made for TV that are 30 frame and 25 frame will use the 352 by 480 or 576. The data rate on this will run anywhere between 2.5 up to 6 megabits, depending again on how good of quality that you want for each application. The last resolution is 352 by either 240 or 288. It's basically half resolution in the vertical domain. These are the resolutions that will be used for cable distribution, for film-based material only, for 24-frame-based material. This type of movie material will be passed at data rates sub 2 megabits and will be used for the near video on demand applications throughout the industry.
The International Standards Organization has established an open systems interconnection model to foster compatibility between various communication networks, including those using MPEG compression. The OSI model defines the functions, services, and protocols involved in the communication process. Each message relayed through a communication system using the OSI model passes downward during transmission or upward during reception through each layer. The application layer serves as the link between communication systems and the outside world. The presentation layer is responsible for delivering the message in a form that the receiving system can understand and access. MPEG features flexible conversion between various video standards and formats, including PAL, NTSC, widescreen, and HDTV. The session layer manages the message assembly, buffering, and information exchange. It also provides for the flexible integration of video, audio, text, voice, and data. The transport layer controls the end-to-end delivery of data, including the multiplexing of multiple messages. It also governs interoperability between the various cable, broadcast, and satellite transmission standards. The network layer routes communications through network resources. The data link layer formats and synchronizes the message. It includes error control and protocols which break up the data bit stream into sequential frames. The physical layer is the interface to the transmission medium. It includes mechanical and electrical interconnections.
The transport layer in MPEG-2 is of considerable importance because it is the layer which carries the information so that a receiver can determine what services of an MPEG nature are carried in a particular bit stream. So without the transport layer, it's much more difficult to have interoperability, and that's the goal of the MPEG-2 standard. Transport layer is simply the way that the bits are multiplexed together so that audio, video, and user data can be taken apart easily at the receiver.
Two different transmission modes are used to deliver MPEG compressed programming via satellite. Single channel per carrier, or SCPC signals, have their own independent carriers and frequency assignments within the bandwidth of a given satellite transponder. MPEG program services using SCPC can uplink their programming from different physical locations while sharing the same transponder. SCPC typically is used for program exchanges, satellite news gathering applications, business and educational networks, or any other part-time service which does not need dedicated 24-hour service.
Spectrum Saver utilizes an SCPC type broadcast. This means that you're able to deliver your programming material from multiple locations, whereas in the past you had to bring your source material to one central location and then deliver that to an uplink facility who would mix it together with their other materials that they're broadcasting. This, for an educational marketplace, allows you to originate your source material at any one of your uplink sites that is located at the university and to deliver it throughout the United States. Currently, here's a 3.3 broadcast, which is delivering educational video for Ball State University, part of the IHATS educational network. Moving on over, we'll see the Westcott Communication Network, which is delivering educational programming material for long-term health care networks. These two demonstrations here show you a 3.3 megabit, which is fine for distant learning applications where you have slow motion, very little movement inside the image there. Whereas in the 6.6 megabit transmission range, you have the capabilities of handling high motion to deliver entertainment quality video.
For the part-time services, we needed an SCPC type of system which would allow for origination from other points beyond my gateway to South America for events within South America. The compromise there is it's not the most efficient loading on a satellite, so dish sizes or the amount of power used for reception of the signal is not optimal. In the case of the DigiCipher service, it's an MCPC where we multiplex 6 individual video channels into one carrier, consuming about 24 megahertz of satellite bandwidth, nominally one normal transponder, which is used to maximize the transponder and allow multiple programmers access through the same system. Again, an individual receiver is needed for each program channel, but the overall efficiencies of the system in terms of power on the satellite and other advantages like multiplexing, where statistical multiplexing, where the individual channels are combined in a way that allows the individual channel that requires more motion compensation for the particular passage of video can borrow from the other channels in the system to provide on-demand kind of additional capacity for motion compensation.
Multiple channel per carrier, or MCPC transmissions, contain 2 or more program services which are multiplexed into a single unified signal. Networks using MCPC can share the same conditional access and forward error correction systems. This economizes on the overall bandwidth and transmission speed requirements for these networks. What's more, programmers can dynamically assign capacity within the multiplex, providing additional bits to a live sports broadcast and fewer bits to a talking head infomercial. At the conclusion of the sports event, excess bits could then be reassigned to another service within the multiplex. If a pay-per-view program generates an unusually high number of orders, bits can be reallocated for decoder authorization. This will minimize the time between the customer placing an order for a program and their decoder being turned on. The main disadvantage of MCPC is that all program services must be uplinked from the same physical location. For example, a 21.5 megabit per second multiplex might include 2 to 10 standard video services, 20 audio channels, text at 45 pages per second, 5 19.2 kilobit per second data channels, and conditional access addressing to millions of decoders. In addition to being a global standard on its own, MPEG-2 forms one of the principal components of a new global digital video broadcasting standard. Called DVB for short, it consists of several sets of interrelated specifications that define just how digital broadcasting will operate over an existing satellite, cable, or terrestrial communications infrastructure. In each and every iteration of the DVB standard, the data is transmitted within transport streams based on the MPEG-2 compression standard, and with the primary differences between subsets having to do with the particular signal modulation scheme in use. The MPEG-2 standard, also known as DVB, was specifically optimized for the transmission of both standard and high-definition television programs. With the rise of the internet, however, the applications for digital video expanded dramatically. More efficient forms of compression were clearly required, with bit rates that could accommodate video conferencing and streaming multimedia to PCs. Moreover, the technology had to be fully compatible with both wireline and wireless networks. Last but not least, the worldwide switch to high-definition television forced the industry to push the compression envelope even further to accommodate HDTV's higher image resolution and 16:9 aspect ratio. Officially known as H.264 or MPEG-4 Part 10, the latest advanced digital coding is squarely built on many of the same tools and techniques to be found in MPEG-2. Satellite broadcasters like DirecTV are using it to transmit their programs in a high-definition format. To ensure interoperability between heterogeneous systems, Advanced Video Coding, or AVC for short, provides for 3 distinct profiles, each with its own unique set of compression tools. The baseline profile contains the simplest tool set of the 3. It is for use by decoders with the least intensive processing requirements, such as video over Internet Protocol or the streaming of TV to mobile handsets. It achieves a 1.5 times improvement in compression over MPEG-2. The extended profile is suitable for use in Internet-capable PCs and sophisticated handsets. It achieves a 2 times improvement in compression efficiency over MPEG-2. The most complex of the 3 is the main profile, which is really best suited for broadcasting applications, since it includes interlaced video tools. It achieves a 3 times improvement in compression efficiency over MPEG-2. Advanced video coding takes compression to the next level by building on the strengths of the MPEG toolset. What follows is a review of some of the improvements that have been made. MPEG-2 limits the available block sizes for motion compensation and prediction to just 16 by 16 or 8 by 8 pixels. By contrast, AVC expands the available range from 16 by 16 all the way down to 4 by 4 pixels to enable small moving objects to be compressed more efficiently and more accurately. Both MPEG-2 and AVC analyze neighboring blocks to accurately predict the vector of motion for objects moving from one location in a picture to the next. However, AVC looks at more neighboring blocks than MPEG, allowing complex motions to be more efficiently represented. AVC also more concisely compresses moving picture areas by enabling the encoder to search for the best match from across multiple previous or future frames of video. AVC also uses a higher efficiency version of the same advanced audio coding technology used in MP3 players. The encoder reproduces perceptually lossless stereo sound at speeds of less than 60 kilobits per second. AVC's brand new tools streamline the compression process even further. One innovative encoding method gathers statistics on the incoming video and then adaptively assigns extremely small bit ratios to the more